Now, there's another issue I want to talk to you about here, and the context in which we should talk about it is dealing with cohort studies. I want to introduce the concept of number needed to treat, often written as simply the letters NNT. Number needed to treat, the term is actually kind of misleading, because often we're not talking about treatment. We could be, but often we're talking about prevention. And so another way to think about this concept is number needed to prevent. The central theme is easy. How many people do we have to reach out and do something to get rid of or stop one case we otherwise would have had? Get rid of would be treatment, stop one case would be the prevention issue. How many people do we have to do something to stop one case? Well, if you think about it, that ought to be related to an incidence rate, don't you think? Because if the incidence rate is fairly high, then doing something to a few people should stop that one magic case I ask you to think about. Where if the incidence rate is fairly low, then we have to reach out and touch a whole lot more people to stop that one magic case. Right. Number needed to treat is directly related to the incidence rate. In fact, it is, in a real sense, the inverse of that incidence rate. If you have an incidence rate, you take the inverse, and voila, you have number needed to treat. It's no more difficult than that. So, why are we talking about this in the context of attributable risk? Well, I remind you, the way you get an attributable risk is take one incidence rate, subtract another incidence rate from it, and that gives you the attributable risk. But that attributable risk, the result of subtraction of two incidence rates, is kind of a comparative incidence rate, right? And so with that attributable risk, we can take the inverse of it, and we have number needed to treat. And even if that last couple of minutes was confusing, let's focus on exactly what you need to do to answer the question. In order to get number needed to treat, you take that attributable risk, the result of subtracting two incidence rates, take the inverse of it, and becomes number needed to treat. An inverse, I remind you, you have numerator, denominator, flip them, and now the denominator is the numerator, now the numerator is the denominator, that's the inverse, and you end up with number needed to treat. Let's try this by concrete example. We have two incidence rates, 8 out of 1,000 and 3 out of 1,000. Well, our first step is to compare them by mere subtraction here. So 8 out of 1,000 minus 3 out of 1,000 gives us 5 out of 1,000. That's an attributable risk. We now have the number that we need. We next take that attributable risk, 5 out of 1,000, and we take the inverse. That means now 5 goes on the bottom, 1,000 goes on top, and then by reductive mathematics, that easily comes out to be 200. That means number needed to treat is equal to 200. What does that mean? Simply, for every 200 people treated, one case will be prevented. For every 200 people we touch, one case we will no longer have to worry about. Remember the issue here, how many do you touch to prevent one case? That's the key issue. What is number needed to treat? The simple thing to remember is that the inverse of an incidence rate, which in this context is the inverse of the attributable risk. Now, there's another similar term, doesn't sound similar, but it's actually the same thing you might run into. It's a term called number needed to harm, sometimes written as NNH, number needed to harm. Well, the point I want you to walk out of here with is number needed to treat and number needed to harm are certainly computationally and practically the same thing. There's a little bit different words we use in interpretation, but what you're going to do with the numbers is the same thing. Instead of the incidence rate in the untreated minus the incidence rate of the treated, what you had here for number needed to treat, for number needed to harm, it's the incidence rate in the exposed minus the incidence rate in the unexposed. But notice you're still subtracting two incidence rates and you're still generating an attributable risk. What you're labeling those incidence rates with may sound different, but the mechanics are purely the same. Instead of treatment, we're looking at exposure here, the mechanics being the same. All we have to do to generate that number needed to harm is exactly what we did before. In this case, the 8 out of 1,000 is the exposed. In this case, the 3 out of 1,000 is the unexposed, which gives us the attributable risk of 5 out of 1,000. We then take an inverse, same thing as before. If this sounds like I'm saying the same thing, that's the point. And then I get 200, which is the number needed to harm in this context. How do I interpret that? Simple. For every 200 people exposed, one case occurs. We're not talking about stopping, we're talking about what makes something happen. And although those are different words, take a look with me, because what I want you to walk out with is number needed to treat and number needed to harm are computationally and practically the same thing. The trouble is, it's two different labels that sound like they're very different things, but frankly, the words are masking what are the similarities. What do you do to generate number needed to treat? You get the difference between two incidence rates on attributable risk, take the inverse, and you have the answer. What do you do for number needed to harm? You take the two incidence rates, subtract them, get the attributable risk, take the inverse, and you have number needed to harm. The same thing. That's how we're going to deal with data that come out of a cohort study. Remember, you can only use attributable risk, you can only use relative risk to deal with cohort studies. Why? Because both of these require incidence data. If you don't have incidence data, you can't do relative risk and you can't do attributable risk. And so you can't use them for a case control study. Why? Yeah, because there's no incidence data in a case control study, as you recall. For this study, case control study, we're going to do something called an odds ratio. And let's put those together as a simple linkage in your head. When you see case control, think odds ratio. When you see odds ratio, think case control. Let's do that again. Case control goes with odds ratio. Odds ratio goes with case control. Put those two together. Now, the odds ratio we're talking about here is, of course, about exposure. Because what we're looking for in the case control study is just that comparison. The odds of exposure with the odds of non-exposure relative to the risk factor. The odds ratio, the name is the definition, just like for case control. The same way case control describes the study, cases compared to control, looking retrospectively for risk factor, odds ratio describes the analysis. An odds ratio is merely the ratio of odds. Let's take a look at that, but before we go there, I just wanted to insert one other issue here to highlight for you. Take a look on the slide before you. Here we have the presentation in a 2x2 table of an observational study. The question I have for you is simple. What kind of observational study is this? Is this a cross-sectional study? Is this a cohort study? Is this a case control study? What kind of study is this? What do you think? Well, the point is, you can't tell by looking. This could be any one of those three kinds of studies. Follow me on this. Suppose right now I go out and I assess who has lung cancer and who doesn't have lung cancer, and at the same time I assess who is and is not a smoker. That would be a, cross-sectional study, and I could present the data just like this. Or suppose I go out and I find out who's a smoker, who's not a smoker, and I follow these people forward over the next 5 years, recording who does and does not develop lung cancer. That would be a cohort study, and I could present the data just like this. Or suppose I go out and I find people who have lung cancer, people that don't have lung cancer. I look backwards in their history for the presence or absence of smoking as a risk factor. That would be a case control study, and please note, I could present the data just like this, right? The point is, you can't tell what kind of study by staring fixedly at that 2x2 table. It's not the data presentation that matters, it's the data derivation that matters. In short, you better read the text that comes with the table to see what they did to get the numbers so you know what to do with the numbers. Remember, what kind of analysis is determined by what type of study that you have. If you have a case control study, that's one kind of analysis, the odds ratio. We'll talk about that in detail in just a moment. If you have a cohort study, that's another kind of analysis, the relative risk or attributable risk. And understand how these questions usually show up in the exam. They do not say to you, here's a cohort study, please analyze the data. They say, here's a study, analyze the data. You're going to have to realize, that's a case control study, in which case I'll pick the odds ratio answer. Or you're going to have to say, that's a cohort study, in which case you pick the relative risk or attributable risk answer. The bridge to which type of analysis is to first determine which type of study. Okay, having made that basic point, I now wave my magic wand and bling, I convert this table we've been staring at into a case control study. How do you know it's a case control study? Because I'm telling you it is. You know because I just defined it for you that way. Okay, now, in this case control study, some simple questions. First, what are the odds of being a smoker given that you have lung cancer? Well, that's easy. The odds are A divided by C. Now please note in this case, not A divided by A plus C, A to C directly. Why? Because that's what we mean by the word odds, a direct ratio of the two cells. Notice, unlike we did the relative risk calculation, it's not the marginal we're looking for here, it's just a direct ratio of the two cells, A divided by C. Okay, if that's the odds of being a smoker given lung cancer, second question, what's the odds of being a smoker given no lung cancer? Well, once again, that should be easy. It's a direct ratio of the two cells, in this case, B divided by D, right? A divided by C, the odds for lung cancer, and B divided by D, the odds for no lung cancer. Oh wait, if A divided by C is an odds, it is, and if B divided by D is an odds, it is, what's the odds ratio? Oh, that's easy. A divided by C divided by B divided by D. Divided by, divided by, divided by. Isn't that just way too many divided bys? Well, you're lucky. Because using the magic of algebraic transformation, we're able to take this definition formula and convert it into a much easier to use computational formula, namely AD divided by BC. And that's the formula to learn. AD divided by BC is how we compute the odds ratio. Let's take a look at that formula together and talk about some ways to remember it. Let's focus on taking it a piece at a time. First, look at the numerator. Above the line, AD. And now, quick, free associate. What comes to mind when I say AD? AD. Ah, well, this is the year 2009, AD, Anno Domini, in the Christian nomenclature. AD, and with that headset in mind, AD, let's look down at BC. BC, that's BC, before Christ, in Latin, but before Christ here. And so, that's how you remember the odds ratio. It's AD, present time, divided by BC, former time. AD divided by BC is your computation for the odds ratio. Simple, should be easy to remember, you should never forget this. Now all we have to do to complete the process is one final step. I have to make sure you know which cell's A, which one's B, which one's C, and which one's D. Wait, this is easy. Because all you have to do is find the A cell. Once you find the A cell, everything else is derivative from that. And the A cell is the cell you probably care the most about. Look, here's a study of smoking and lung cancer. Be honest, where do your eyes tend to go first? Isn't it the smokers and the lung cancer together? Well, the risk factor with the disease convergent, that's always going to be your A cell. In this case, smoking with lung cancer, that's the A cell. And then D, D stands for diagonal. D is the diagonal cell. Once you find the risk factor in the disease, D is the diagonal cell. And then B and C is simply what's left over. Wait a minute. Which one's B and which one's C? Right. Remember, you're multiplying them together. It doesn't matter. Who cares? Worry about something that matters. That one doesn't. Notice we're multiplying together the diagonal cells for our computation. In technical language, we call these the cross products. It's AD divided by BC, the formula for the odds ratio. Easy to compute. Literally a back-of-the-envelope calculation, and easily something you could be asked to do on your Step 1 exam. Let's try an example together, shall we? Here we have a 2x2 table, which is giving the results of a case control study. Notice you know it is because the title tells you it's a case control study. You have family history of colorectal cancer, no family history of colorectal cancer, no colorectal cancer, colorectal cancer. Quick, which is the A cell? Notice something. I've rotated the table a little bit on you, haven't I? 120 is not the A cell, 60 is the A cell. That would be disease and risk factor together. If 60 is the A cell, then 200 must be the D cell, that's the diagonal cell, and then 120 times 20 is the B and C multiplication. So using this data, AD over BC, the computation for the odds ratio is 60 times 200 divided by 120 times 20. Now often on your exam, just setting up the problem like that, that's all you need to code the answer. Why? Because if you make a stupid math error multiplying that out, that's a bad exam question. Because they don't care how good you are in math. You're old enough, nobody cares anymore. All we care about is that you understand the concept, and showing you can set it up right is how you're demonstrating the concept. But if we were to multiply this all the way out, we would get an odds ratio equal 5. Odds ratio equal 5. What does that mean? Well, you're going to hear this read interpreted in different ways. One way you're going to hear this read interpreted would be, if you have a family history of colorectal cancer, you're 5 times more likely to have colorectal cancer yourself. Now, that's correct, but it's not best. Why is it not best? Because it's not really truly honest to the data you have. Yes, I know many of you want to look at family history and predict colorectal cancer, but in this case control study, that's not the data you collected. The data you collected was you started with colorectal cancer and then you went back and looked at family history. And so read the odds ratio like that. We're not talking about the chance of having colorectal cancer here. We're talking about the strength of the risk factor. The way I'd read the odds ratio is, if you have colorectal cancer, you're 5 times more likely to have had a family history. It's not a prediction of disease, it's an estimate of the strength of the risk factor. Now, let's also reflect for a moment, because the key comparison you're doing in a case control study is cases, disease, versus controls, non-disease. Well, I can therefore look at not a single risk factor, but I could look at multiple different risk factors, right? In the present instance, I could look at, as we have here, family history versus no family history, but I could also look at male versus female. I could look at people born before and after a certain date. I could look at people that live in and outside a certain area. I could generate a whole lot of different risk factors, every one of which I could use to construct a separate 2x2 table, and for every separate 2x2 table, I could compute a separate odds ratio, right? And the odds ratio out of all those tables that is the largest would therefore be my number 1 risk factor. Now you've heard the term. You've used it yourself, number 1 risk factor. How do we get the number 1 risk factor? It's a result of a series of odds ratio computations from a case control study, and the risk factor that gives us the largest odds ratio is our number 1 risk factor. So, quick review. In a case control study, we're comparing disease versus non-disease, looking backwards for the presence or absence of a risk factor. We evaluate the strength of that risk factor by computing an odds ratio. Odds ratio goes with case control study. What's the formula for the odds ratio? AD divided by BC. What's the A cell? Disease and risk factor convergent. What's the D cell? Diagonal from the A cell. B and C is simply residual, what's left over. What do I get when I do this odds ratio computation? Simple. I get a specific number that answers the question, how important, how strong is the risk factor? The larger the odds ratio, the more important the risk factor. At the end of this section, I want to direct your attention to the summary table, which presents to you once again in organized form some of the key distinctions we've already talked about here. I want to draw your attention to the